questions 8 through 10 on the 2012 Grade 12 Euclid Math Contest. On Saturday, Jimmy started painting his toy helicopter between 9 a.m. and 10 a.m. When he finished between 10 a.m. and 11 a.m. on the same morning, the hour hand was exactly where the minute hand had been when he started, and the minute hand was exactly where the hour hand had been when he started. Jimmy spent T hours painting to determine the value of T. Now, this is, of course, the start, and this is the finish, so before and after. And we are told some very interesting information, and the diagram also depicts that the hour hand, which is here, and the minute hand, which is here, we sort of are reversing them. So the minute hand takes the place of the hour hand, and the hour hand takes the place of the minute hand. So they want you to figure out how long does it take essentially for that to happen. So what we can do is look at it from the perspective of angles, and in particular inside there. So the hour hand is right here initially, and then it eventually goes there. So it's moved from there to there. So that little guy I will call X, that angle. And then the minute hand, which was originally here, will go all the way around, right? And then end up right there, which is depicted here. So that means when it goes all the way around, it goes 360 degrees minus X. That is the distance that it travels. So let's just put that here. The hour hand moves X degrees, and the minute hand moves 360 minus X degrees. Now, keep in mind that the hour hand moves 1/12 of the clock every hour in 1 hour. And that hopefully makes perfect sense, right? Every hour it moves 1/12 of the clock. So for example, from 7 to 8 or 8 to 9, each of those represent 1/12 since there's 12 hours. But the minute hand in 1 hour moves the full distance of the clock, right? If you were here, the minute hand in 1 hour will go all the way around back to the same place. So that basically means if you make a comparison between the minute hand and the hour hand in 1 hour, the minute hand is moving 12 times as quickly as the hour hand. So that means that this minute hand, if you compare it to the hour hand, has moved 12 times. So if you look at those two values, that would mean that 360 minus X over X has a ratio of 12 to 1, because the minute hand moves 12 times as quickly as the hour hand. So this is basically what it boils down to, this equation. So solving for this, if you cross multiply, you get 360 minus X is equal to 12 X, and therefore 360 is equal to 13X, and therefore X is equal to 360 over 13. And you can convert that to decimals if you want. It'll be 27 point something. Okay, we got X, but we have to figure out T. T is the time. Well, to figure out the time is basically represented by this guy. That is the time. And that actually giving you a degrees, but once you have the degree, then you can just easily figure out what is the time in terms of hours by dividing by 360. So I'll show you. If X is this, then that means 360 minus X is this distance that the hour hand travels. And the distance the hour hand travels will be 360 minus 360 over 13. And this is going to be equivalent to 12 over 13 times 360. What this represents is basically the degrees that the minute hand travels when it goes from there all the way to there. and that's approximately 332 degrees, 0.3. But we want the time. Well, one full rotation would be 360 degrees for 1 hour. But this is not 360, it's a little bit less. So to figure out how many hours, we would just take that and divide by 360. And that would give me how many hours. And when you do that, you get 0.923. And this basically, if we were to keep everything in fractions, I made it into decimals because it usually is a little bit easier to understand. But if you kept it in fractions, you'll notice that this is just 12 over 13. And that is my value for t. Determine all real values of x such that this expression is true. So we have the log to the base 5x plus 9 to x squared plus 6x plus 9. But I think I can factor that. X plus 3, x plus 3. And then I have log to the base x plus 3. And then this expression, 5x squared plus 24x plus 27, I think that can factor. X plus 3 and 5x plus 9. And of course, don't forget that 4. So as you can see, you're starting to see some common terms, which is a good thing. At least I hope. We'll see what happens. Okay, well, this part here, log of 5x plus 9, this is x plus 3 to the power of 2. But we all know from log rules that that 2 can be placed out front. So let's put it out front, save a step here. And then this, from log rules, can be broken up. It can be log of x plus 3 for x plus 3, and then we can break it up plus log to the base x plus 3 of 5x plus 9. And that all equals 4. Okay, now at this point, this guy in here is just 1, and this here doesn't change. The rest doesn't change. Okay, now at this point we have to use a log rule. It's a very helpful log rule, and that is that the log of a to the base b is equal to 1 over the log of b to the base a. And that's applicable because, as you can see, we've got that kind of a situation here. We can use that log rule. So for example, the log of 5x plus 9 to the base x plus 3 is equal to 1 over the log of x plus 3 to the base 5x plus 9. And that's going to be very helpful. And to make things even more simpler, what I'll do is I'll call this guy here k. This I'll just represent with the k. So this becomes 2. This I have called k, so just 2k, and then plus 1, and then plus this, but that is equivalent to 1 over k. And that equals 4. Now multiply through by k, and we get 2k squared plus k plus 1 is equal to 4k. And then this becomes 2k squared minus 3k plus 1 is equal to 0. And we can, of course, factor this. And we get 2k, k, 1, 1, and minus, minus. Yeah, that'll do it. And this gives us very helpful solutions that k is either equal to 1/2 or it is equal to 1. And remember, I had denoted this as my k, so now all I have to do is just solve that. So that k was log of x plus 3 to the base 5x plus 9, and that is equal to either half or 1. Okay, so let's do half first, this guy. Let's set it equal to 1/2 and see what happens. Then by log rules, that means 5x plus 9 to the half is equal to x plus 3. Square both sides and you get 5x plus 9 is equal to x squared plus 6x plus 9. And then let's see here, if I put everything on one side, I get x squared plus x is equal to 0. Factor out the x and I get x plus 1. And therefore from this I get x is equal to 0 or negative 1. So that takes care of this k equals a half, but I still have to do k equals 1. So that means the log of x plus 3 to the base 5x plus 9 is equal to 1. 5x plus 9 to the power of 1 is equal to x plus 3 according to basic log rules. And that means 4x is equal to negative 6, and x is therefore equal to negative 6 over 4, or in lowest terms, minus 3 over 2. And there you have it. X is equal to either negative 3 over 2, or 0, or negative 1. Those are the three solutions to question number 8b. An auditorium has a rectangular array of chairs. There are exactly 14 boys seated in each row and exactly 10 girls seated in each column. If exactly 3 chairs are empty, prove that there are at least 567 chairs in the auditorium. Well, you have some rectangular arrangement of chairs, and you have obviously rows and columns. And from the question, we are told that each row has at least 14 boys. So there's going to be 14 times R boys in total. Each column has 10 girls, so there's going to be 10 times C, which is the number of columns, girls. And then there's 3 empty seats. So this is the total number of seats. 14R plus 10C plus 3. Now, if you just look at this rectangle, the number of seats is going to be R times C. R rows and C columns, so the number of seats is R times C. So that means that this has to be equal to RC. So that is the setup of the question. Now we have to look at some parameters though. C is the number of columns, right? So in each row there has to be at least 14 of these boys. So C must be at least 14. So C's got to be greater than or equal to 14. By similar logic, in each column there's 10 girls. So that means R has to be at least 10. So R has to be at least greater than or equal to 10. Okay, so we have to come up with solutions to this that involve integers for R and C with these parameters in mind. So here we go. RC is equal to 14R plus 10C plus 3. Okay, rearrange this, bring our 14R over, and if you do, you get 14R on this side, 10C plus 3 on that side. Factor out an R, and you get C minus 14. And I can now put that in the denominator like this, 10C plus 3 over C minus 14. Okay, we're trying to come up with an easy way to figure out what is R and what is C. But this is one of those questions that involves a little bit of an algebraic trick. And in particular, with this 3, we're going to break up that 3 into minus 140 plus 143, like that. And when you do that, that allows us to make this expression a little bit more easier to handle. So that basically brings me to the conclusion that R, if you break this up, is going to be 10C minus 140 over C minus 14 plus 143 over C minus 14. And this guy here factors further into 10 times C minus 14 all over C minus 14. And that part is still 143 over C minus 14. And then the c minus 14s cancel top and bottom like that. So you're just left with 10 plus 143 over c minus 14. All right. So at this point, hopefully, we can now figure out what is integer solutions to this question. Well, r is an integer, right? Because r represents the number of rows. And c is also an integer, it represents the number of columns. So the only way that r is going to be an integer in this equation is if this is an integer, because 10 is already an integer. So we have to somehow make 143 divided by c minus 14 an integer. Well, how do we do that? R is equal to 10 plus 143, but that's 11 times 13 all over c minus 14. That means that c minus 14 has to divide into 143 in some way. So let's make a table. Let's figure out what is c minus 14, our possibilities, and then what is c, and then what is r, and then finally what is r times c. Well, c minus 14 could be 1, right? That would divide 143. c minus 14 could be 11. That would divide 143. It could be 13, or it could be 143. If c minus 14 is 1, c will be 15. And if it's 11, c will be 25. If it's 13, 27, and 143, 157, right? Now r, to get r, we have to substitute our value for c back into there, or c minus 14, probably a little faster. You get 153, you get 23 for this, 21, and 11. And now finally r times c, you get 2295, 575, 567, and 1727. So as you can clearly see, there are at least 567 chairs in the auditorium. That's the minimum number. It could be greater, it could be 575, it could be 1727, or it could be 2295. But the minimum number of chairs in order for this all to work according to the question stem and their criteria is 567. In the diagram, quadrilateral ABCD has points M and N on AB and DC, respectively, with AM over AB equal to NC over DC. Line segments AN and DM intersect at P, while BN and CM intersect at Q. Prove that the area of quadrilateral PMQN equals the sum of the areas of APD plus BQC. We have to prove that PMQN is equal to the triangle APD plus the triangle BQC. Now, that is equivalent to proving the following. PMQN, if I'm going to prove that, is equal to this, well, I can just add a few things on either side. So let's first put in the APD plus BQC, right? That is definitely valid because that's what they want us to prove. But if I put, let's say, a plus 3 here and a plus 3 here, that's also valid as long as I add it to both sides. So what I'm going to add to both sides first is DPN. Let's put that over here, DPN. And then I'm going to add also CQN. So let's put that over here, CQN. Now, what that allows me to do is combine. This all combined, if you look at the diagram, is the same as the big triangle DMC, right? And then DPN plus APD, these two guys, if you look at the diagram, APD is right here, DPN is right here. Those two combined are the same as DAN, that triangle. And then BQC plus CQN, if you look at the diagram, if you combine them, is the same as triangle CBN. Okay, so that is the same. If I can prove that, I can basically say that that is proven. So this is how we proceed. Now in this diagram, we will label a few things. I'm going to draw an altitude from A down to the bottom right here. I'm going to draw another one from M down to the bottom, and another one from B down to the bottom, like that. And those are my heights, basically. And let's label this. The one from A down to the bottom, I will call A. The one from M down to the bottom, I will call that height M. And the one from B down to the bottom, I will just call B. And then I also need to label the base from there to there. The whole distance from D to C, I will call X. And the distance from D to N, from here to here, I will call some fraction of X, Tx, like that, where T is basically between 0 and 1. So it's like 0.7. So that'd be 0.7x. And therefore, N to C would be 1 minus T times X. Okay? So this is just some basic labeling. And then I use those labels to now proceed with this equation. DMC is basically going to be 1/2 base times height. The base is X, and the height for DMC is M, according to how I've labeled it. DAN, according to how I've labeled it, the area of that triangle will be 1/2 base, which is 1/2 times Tx times the height, which is A. And then CBN, according to how I've labeled it, is 1/2 base, which is, in this case, 1 minus Tx times the height, which is B. All right. Now let's try to simplify this. First thing you can do is get rid of all the halves, and that'll just give you xm is equal to Txa plus 1 minus Txb. And then you notice the x's cancel for everything, so that just leaves you with m is equal to Ta plus 1 minus T times B. And that's it. So we have to prove this. If we can prove that, then we have proven that this is equal to that, which is what they want you to figure out in the original question. Now, go back to the diagram and let's draw a horizontal line from A all the way across like that. Now, once we draw in that horizontal line, I have to label some points now. This top to bottom, I will call E. This top to bottom, I will call F, those points. This one I will call G. And then that horizontal line, as you can see, it touches A, but it crosses that line MF and right there. So that point I will denote as R, if I can squeeze that in there, this point right here. And then it crosses this line also, that point right there, and that point I will call S, if I can squeeze it in. Okay, so horizontal line meets MF at R, and it meets BG at S, and I have labeled that as well. So now that means the distance from M to R is basically the same as M minus A, right? This M minus A will give you that tiny little distance from M to R. And then in a very similar way, the distance from B to S, which is that distance right here, will be the same as B minus A. This B, that height, minus that height. Okay? So now we are in the final stage of the question. And here we go. Now we have to look at two triangles, and those two triangles are ARM. and the triangle ASB. And those two triangles are similar. So ARM is this little guy, and ASB is that bigger triangle. Because they're similar, the ratio of the sides will be the same. So that means MR over BS will be the same as AM over AB. All right? So that's straight from similar triangles. But from the question, we have a very important relationship that we haven't used yet. That is AM over AB is equal to NC over DC. AM over AB is equal to NC over DC. Now you might have wondered, when is that going to come into effect? Well, it just did. So that means since MR over BS is equal to AB over AM over AB, and AM over AB is equal to NC over DC, you can see where this is going. That means this is equal to that, if you just follow that chain of equality. So that means that MR over BS is equal to NC over DC. All right? No tricks in this question, interestingly. And then now we can substitute everything that we've labeled for this guy. MR, what is MR? It's M over A. So put that there, M over A. BS, what is BS? It's B over A. So put that here. And that's equal to NC over DC. Well, what is NC? NC is from there to there, which we had previously labeled as 1 minus t x. So 1 minus t times x. And DC is all the way from there to there, which we had previously denoted as x. All right, so this is where we are now. This x cancels with that x, so all we're left with is just m over a. M minus a over b minus a is equal to 1 minus t. If you cross multiply, you'll get m minus a is equal to b minus a times 1 minus t. Expand this all out, and you get m minus a is equal to b minus bt minus a plus at. As you can see, minus a's cancel from both sides, and the only thing you're left with is just m is equal to b minus bt plus at, and then you can factor out a b, and that gives me 1 minus t plus at. And there you go, you're done. You just proven this, and that's what this is. We had to prove this, and we did by coming up with that. Those are identical. That's equal to that. So there we go. We just proved what they wanted us to figure out in the question, that PMQN is equal to APD plus BQC. For each positive integer n, an Eden sequence from 1, 2, 3, ... until n is defined to be a sequence that satisfies the following conditions. Each of its terms is an element of the set of consecutive integers 1, 2, 3 until n. The sequence is increasing, and the terms in odd number positions are odd, and the terms in even number positions are even. For example, the 4 Eden sequences from 1, 2, 3 are 1, 3, 1, 2, 1, 2, 3. Determine the number of Eden sequences from 1, 2, 3, 4, 5. Well, we can do this. Let's just make a little bit of a system. Let's first find the number of sequences that have only one digit following the pattern. So that's going to be just 1, 3, or 5. Right? This is the numbers I have to choose from. In the first position, since that first position is 1 and 1 is an odd number, I can only put odd numbers. And that's why 1, 3, and 5. Now let's talk about sequences that have two digits in it. So something like this, right? That had 2. Okay. So we've got the first position, which is an odd position, right? Because it's position number 1, and 1 is odd. The second position, position number 2, 2 is an even number, so even numbers can go there. Okay, let's do this now. 1 and 2, that would satisfy it. 1 and 4. 3 now, 3 and 4, and I believe that's it. Okay, let's move over to now 3 digits in my sequence. And now I've got, again, odd, even, odd. That's how I can do it now. Okay, so I believe 1, 2, and 3 will work. 1, 2, and 5 will work. 1, 4, and 5. And I can squeeze in the 3, 4, 5. That will also work. Now, how about if you have 4 numbers? The only one is going to be 1, 2, 3, 4. And if I have 5 numbers, the only one that's going to work is 1, 2, 3, 4, 5. These are the only Eden sequences. So how many did I get? I got 3 here, that's 6. Another 4, that's 10. And then 11, 12. So I got 12 Eden sequences for n equals 5. So I can write it in their notation En, and for n equals 5, right? So that would mean e to the 5 is equal to 12. That's how many Eden sequences I found. For each positive integer n, define e to the n to be the number of Eden sequences from 1 to n. If E17 is 4180 and E20 is 17710, determine E18 and E19. All right, so that's going to be a bit of a challenge. We have to come up with some formula for e to the n, and then use that formula to figure out E18 and E19. Okay, how do we do that though? We have to have some sort of a system, and I will present the system. The first is, in the sequence, any sequence that is just one by itself. How many of those sequences are there going to be? Well, obviously, there's only one such sequence, just one itself. Okay, that's pretty straightforward. Let's go to the second type of sequence, and that is a sequence that begins with 1. So 1, 2, like remember before we had 1, 2, 3, that's a type of sequence that begins with 1, but it has to have more than one term, otherwise it would just be that guy. Okay. Well, this was just 1, but this one I don't know. I have to come up with what is this going to be. But the third possible sequence, in terms of its description, is sequences that do not begin with 1. All right, so now that we've got this little system, how do we now go about to figure out what is the number, generally speaking, for e to the n? Okay, well, e to the n. What we can do is very similar to part A, is figure out values of e to the n for small numbers. N equals 1, 2, 3, 4, 5, 6, like that. It won't take us that long, and my hope is that when we do that, we'll get a little bit of a pattern. And once you get a pattern, then hopefully we can see what to put here and what to put there. All right, here we go. So first one, e to the 1. What is that going to be? Well, e to the 1, if this is my first type, and this is my second type, and that's my third type, there's only one such sequence, as that's just 1 by itself. So there really isn't much to e to the 1, really. E to the 1 is really just equal to 1. So that's it. Now we turn our attention to e to the 2. Shouldn't be that difficult. Of course, in the first category, it's just 1. Second category, we have to come up with sequences now that begin with 1 but have greater than one term. Let's see here. For that, I think there's only one possible sequence. That's it. So we have one sequence here, and therefore e to the 2 is just 2. There's no such sequence that begins with something other than 1 for e to the 2. Now let's turn our attention to e to the 3. That one, this of course is always 1. E to the 3, we can get 1, 2, or 1, 2, 3. And for the third category, just 3 by itself. That would mean 1, 2, 3, 4 is the value for e to the 3. Okay, moving right along. How about e to the 4? This, of course, is always 1. For the next category, 1, 2, 1, 4, 1, 2, 3, and 1, 2, 3, 4. That should do it. And then for the third category, for e to the 4, 3 and 3, 4. So how many is that? Let's see here. That's 7. Okay. Now, in addition to keeping a tally up top, I'm also going to keep a tally here. For example, this is 1, this is 2, the number of sequences, this is 1, and this is 4, and this is 2. And these are all 1s, right? These ones, so there's no reason to really put them in. Okay, now let's go to E5. E to the 5 I had done in part 8, so we're an expert on that one. We already know that it was 12, and then we had even written out all of them, so you just copy it from what you did earlier. It was 1, 2, 1, 4, 1, 2, 3, 1, 2, 5, and let's see here, 1, 4, 5. And then we also had 1, 2, 3, 4. And then we had 1, 2, 3, 4, 5. Like that. So this is, so far, let's see here, that's 7. For the third category, for E5, we had just 3, 5, 3, 4, and 3, 4, 5. I believe those are the only ones. So that gives me 4. All right. Well, I'll do one more and then we'll talk about the pattern. You can keep going if you want, E7, E8, but I think if we go to E6, that should be enough to figure out or at least explain the pattern. Okay, E6, this is of course just 1. And for E6, we have a whole bunch of these. In the second category, we have 1, 2, 1, 4, 1, 6. We have 1, 2, 3. We have 1, 2, 5. And we have 1, 4, 5. And then we also have 1, 2, 3, 4. 1, 2, 3, 6. 1, 2, 5, 6. 1, 4, 5, 6. And we have 2 more. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. So how many is that? That looks like 12. Okay, so there's 12 there. And then the third category for E6, we have 3, 5, 3, 4. We have 3, 6, 5, 6, 3, 4, 5, and we have 3, 4, 5, 6. So how many is that? That is 7. Okay. Now, like I said, you can keep going, but I think we will stop there to explain the pattern. So let's add up for E6. It looks like 7 plus 12 plus 1, 20. Okay. So here is the, in my opinion, quite challenging way, a quite challenging pattern to recognize, but it's question number 10B. It's the very last question on the senior level exam. So we have to figure out what goes here, what goes here. What goes here, if you notice, is for any e to the n, the number that goes here is e to the n minus 1. And for any e to the n, the number that goes here is e to the n minus 2. So, for example, when n was 6, what one here? The same as e to the 5, right? When n is 6, this would become 6 minus 1, which is e to the 5. So when n is 6, what one here? E to the 5. E to the 5 was 12, and this is 12. Okay, let's see what goes in here. That would be e to the 4, right? When n is 6, this becomes 4. So what would go here is e to the 4, and e to the 4 is 7. See, so you see how that works? Let's try one more. What about when n is 5? When this n is 5, what goes in here? Well, that would be e to the 4. So when n is 5, what goes here is e to the 4, and e to the 4 is 7. That's why this is a 7. When n is 5, what goes in here? Well, that would be e to the 3. So this would have to be e to the 3, and e to the 3 is 4. And that's why this is a 4 here. So that is the pattern. Quite challenging. Well, I think when you see it, you think, oh yeah, that makes sense. But coming up with it on your own, I think is quite daunting. But it's not impossible. There are students who got it. So now we have to come back to the question and calculate these guys. We have to calculate E18 and E19. Okay, so our formula is e to the n is equal to 1 plus e to the n minus 1 plus e to the n minus 2, according to everything that we did. So that means e to the 20 is equal to 1 plus e to the 19 plus e to the 18. Exactly based on that formula. Well, e to the 20 they gave me in the question, it's 17710 is equal to 1 plus e to the 19 plus e to the 18. Okay, so far so good. Now, we don't know either value, so obviously we have to have another equation to help us. Using the same equation, let's try E19. That would be equivalent to 1 plus E18 plus E17. Well, E19 we don't know, but we do know E17, that's been given to us 4180. So that is plus 4180, like that. Okay. Well, now we've got two equations. We got this guy, and we have this guy, and we can solve. So from the first one, I can isolate for E19. From this equation, I can isolate for E19. It would basically be 17710 minus 1 minus E18. That would be E19. That's why I placed it there. And then that is equal to this. So that's going to be 1 plus E18 plus 4180. And we can solve that now. If you bring the E18s over, it becomes 2E18. And then this is just basic numbers, 17710 minus 1 minus 1 minus 4180. And if you do all that math, you get 13528. And then divide through by 2, and you get for E18 a value of 6764. So there we go, we just got E18. And then to find E19, well, E19 is equal to this right here. So E19 would basically be equal to 1 plus E18, which is 6764, plus 4180, and that is equal to 10945. So there you go. Those are the answers to this very challenging question. E18 is 6764 and E19 is 10945 based on the pattern that we identified, that e to the n is equal to 1 plus e to the n minus 1 plus e to the n minus 2.